Hey guys, this is Professor Janacek, and today I want to talk about graphing functions. Now there are several approaches to this. I'm just going to hit four main topics here. We'll start with intercepts, both x and y intercepts, and we'll use some algebra to compute these. We'll also take a look at extrema. We'll use the first derivative test. Sometimes you can also use a second derivative test, but we're going to stick to the first derivative test here. For the inflection points, we'll use the second derivative test. There is also a third derivative test that you can use sometimes, but we'll stick to the second derivative test. And then finally, asymptotes. We'll look at both vertical asymptotes and horizontal or oblique asymptotes. Now there are also some algebraic techniques you can use here. We'll use a little bit of both algebra and calculus for that. All right, so let's dive right into an example here. We've got the function f of x is equal to 4x over x squared plus 3. Now, to get started, since I know I'm going to use the first and second derivative tests for the extrema and inflection points, I've gone ahead and computed the first derivative. Notice that we'll have to use the quotient rule here, and then I do end up factoring out a 4 in the numerator, just in case we need it. It looked like we might be able to reduce that. Turns out that we couldn't. So using the quotient rule to find the first derivative and the second derivative, you'll notice this one is much longer. There's lots of kind of algebra going on in here, working with those rational expressions and combining terms. But it really, again, in general, it's just the quotient rule. But like I said, there's lots of algebra in there. All right, so now that we've got our first derivative and our second derivative, and of course we will have to reference that function. Make sure you remember those. Make sure you know which one's which. Don't get them confused. All right, so to start with, let's take a look at the intercepts. To find the x-intercept, you simply let y equal to 0. When we do that, again, notice I'm doing this in the original function. There's my original function. Of course, f of x in this case is my y value, and I replace that with 0, and then we solve for x. And so when y is 0, we get the x value 0, so there is an x-intercept at 0, 0. Now, 0, 0 is also, the origin is also a y-intercept, so you don't necessarily have to go through this. You can simply say, well, there's only one y-intercept and we've already found it. However, if you want to, you can go through the process for all y-intercepts. The x value is 0. Again, going to our original function, the y value we get from that, we simply replace x with 0 and we get a y value of 0 as well. So the x and y-intercept in this case is the same. It is the origin. All right, so now on to the fun part, extrema. So we are going to use, of course, the first derivative test. So we'll begin by finding the possible extrema. We call those critical values. We start by letting the first derivative, f prime of x, be equal to 0, or let it be undefined. When it's equal to 0, notice again I'm looking at the first derivative here. Setting it equal to 0, notice I really just have to take that numerator and set it equal to 0. And then when we solve that, again, I didn't show all of that arithmetic, but you should be able to do that. I say arithmetic, algebra. You should be able to do that little bit of algebra there, and we get that x is either a positive or a negative square root of 3. Now, for f prime to be undefined, looking at that, since f prime is a rational expression, that is undefined when its denominator is equal to 0. So I take the denominator, set it to 0. Again, use a little bit of algebra there, and we actually get that x is a positive or negative I square root of 3. Notice because we will end up taking the square root of a negative. So we get an I in there. Now, these are imaginary, so those are not going to be on our graph. We will not worry about graphing imaginary numbers. So, turns out our only critical values, critical numbers, critical points, if you want to reference them as points on the x-axis, are those two, x is equal to a negative square root of 3 and x is equal to a positive square root of 3. Now, using the first derivative test, we'll have to pick something to the left and right of each of those. So let's start with just the negative square root of 3. I'm going to pick something to the left and to the right. Well, because it's negative, I have to think about it in the negative direction. It is good to remember that we can approximate the square root of 3 as 1.7. So negative square root of 3 is about negative 1.7. So to the left, I'll pick negative 2, and to the right of any negative number is 0. I do need to be careful. I don't want to go so far as to pick something that goes past the other critical value. So I can't pick something like positive 2 because that would pass up my other critical value. So these left and right values have to be in between the critical values. All right, so again, picking the left-hand value to be 0 and the right-hand value to be, the left-hand value to be negative 2, the right-hand value to be 0. What we do with those, remember, is we actually plug those values into the first derivative. Again, this is the first derivative test. So we put negative 2 into the first derivative. Now, I didn't show all that computation there. You should be able to do this without a calculator. Take your time with that. What we end up with, the important thing is that it is less than 0. So the first derivative is less than 0. Remember, the first derivative tells us if our function is increasing or decreasing. So that tells us that it is decreasing on the left. Similarly, we'll take the r value of 0 and put that into our first derivative. And again, I don't go through all that computation. You should be able to do this on your own. However you look at it, you should end up with a positive value. So we're looking at something that's greater than 0. Well, if the first derivative is greater than 0, that tells us our function is increasing. So it's increasing to the right. So decreasing to the left and increasing to the right, well, if we look at what's going on there, that looks like there's going to be a minimum. So we know that there is a minimum at x equal to negative 3. I went ahead and determined the y value quickly there. So the y value, of course, notice to find the y value, I now use the function f, not the derivative. So evaluate that function, and I end up with a y value to go along with that x value. Now we can go through the same thing for the other critical value, so that takes care of this one. Now we have to take a look at the other one. So for the other critical value, x equal to positive square root of 3, we're going to let L equal to 0 and R equal to 2. So notice I'm picking the left-hand value here is the same as the right-hand value there. Again, it has to be in between, and I've already calculated the first derivative here, so it's going to make life really, really simple. And then looking for something to the right of square root of 3, again, since the square root of 3 is approximately 1.7, 2 is a little bit bigger than that, so that's going to work just fine. Remember, we take these values and put them into the first derivative. So evaluate the first derivative at that L or at 0. Again, we already did this here, and so we end up with the exact same thing. So again, we have a positive here. The first derivative is positive, tells us that it is increasing, and we're looking on the left-hand side. On the right-hand side, we evaluate the first derivative at 2, at positive 2. Notice if we put a positive 2 into the first derivative, we actually end up with a negative value. So the first derivative is negative. That means it is decreasing, and we are looking here on the right. So increasing on the left, decreasing on the right. What does that give us? Put that together, and it looks like there is a maximum at that point. Again, we were talking about the x value of square root of 3. So calculate the y value. Again, notice that I am calculating the y value using f, not f prime. And that gives us the y value that goes along with our x value. So moral of the story, along with our two intercepts, we now have that there is a local minimum at negative square root of 3, comma, negative 2 square root of 3 over 3, and a local maximum at square root of 3, comma, 2 square root of 3 over 3. All right, moving on. Now let's take a look at our inflection points. So for the inflection points, we're going to use the second derivative. Again, we'll take the second derivative and set it equal to 0, and also see when it is undefined. Now our second derivative looks something like this. Remember, this is a rational expression. Rational expressions are equal to 0 only when their numerators are equal to 0, and we can easily solve that, set each factor to 0, and we get x is equal to 0, x is equal to 3, and x is equal to negative 3. We also need to remember to determine when that second derivative is undefined. Well, this again is a rational expression. It is undefined when its denominator is equal to 0. The denominator is equal to 0. If we solve this using a little bit of algebra, we get, oops, there should be an I on that one. Must have gotten erased. These are, again, imaginary. So, since these are imaginary, we do not need to consider those for our points of inflection. So, all in all, we have 3 possible points of inflection. X is equal to negative 3, x is equal to 0, and x is equal to positive 3. So we're going to do the same thing with this. For each one of these, I will pick a number to the left and a number to the right and evaluate our second derivative at those. So for x equal to negative 3, I pick negative 4 and negative 2. Evaluate the second derivative. We see that on the left, it is negative, which tells us it is concave down. And on the right, it is positive, which tells us it's concave up. So it's concave down on the left, concave up on the right, must mean that we have an inflection point. Of course, we have to figure out the y value, so when x is negative 3, the y value ends up being negative 1. Again, don't forget, make sure you're using the function value, not the derivative or second derivative. For the next possibility, x equal to 0, we'll pick something to the left and something to the right. I'm going to go ahead and again pick the value to the left that I just used up there to the right. It's going to make my computations a little bit easier. Now, I don't show those computations, but we put them into the second derivative, right? Evaluate that second derivative at these numbers. To the left, it is positive, which means it's concave up, and to the right, it's negative, which means it is concave down. So one side is concave up, one side is concave down, must mean we have an inflection point. Now, the x value we were looking at was 0, so then we have to find the y value that's associated with it. Again, don't forget that y value comes from f of x, not from its derivatives. Finally, we'll do the same thing for x equal to 3, our last possibility. And quite simply, you can see it works very easily that we pick the left-hand value is 2, the right-hand value is 4. Put these into our second derivative. Yes, it takes a little bit of time to come up with that, but evaluate the second derivative at 2. Take your time. Don't use a calculator. You'll get a negative, which means it's concave down on the left. And then if we evaluate the second derivative at 4, we get a positive, which tells us that it's concave up on the right. Again, take your time with those computations, no calculators. Again, concave down on one side, concave up on the other. There we have an inflection point. And then let's find that y value. Again, we simply evaluate the function at that x value, which is 3. So we end up with inflection points of -3, -1, 0, 0, and 3, 1. Okay, Now on to our asymptotes. To find the vertical asymptotes, you can simply look at when the denominator is 0. That gives us possible vertical asymptotes. Of course, we've seen already that this denominator is only 0 for imaginary values of x, so that tells us that there are no vertical asymptotes. For horizontal asymptotes, there are some algebraic techniques that you can use, but let's go ahead and talk about these in terms of the limits. If I take the limit as x approaches positive infinity, notice I am using a little algebraic technique here, multiplying by 1 over x squared divided by 1 over x squared to rewrite this rational expression. Then I can take its limit easily and we actually get that the limit is 0. So this is something we've talked about. It's been a little while, so you might need to review your limits. We do the same thing with the limit as x approaches negative infinity. It actually works out exactly the same way, and we get that the limit as x approaches negative infinity is also 0. So going to the right, we go to 0. Going to the left, we go to 0. That means that there must be a horizontal asymptote at y equal to 0. Again, you could have used some algebraic techniques looking at the degree of the numerator and the degree of the denominator as well. I just wanted to remind you, since this is calculus, how to use limits to think about that as well. All right, so now putting all of this together, oh my goodness, here we go. We can take a look at our graph. Now I've already got the intercept, the extrema, even the points of inflection, and our asymptote. All of that I've already put in here. Again, don't forget, I am using the approximation that the square root of 3 is close to 1.7. And again, you should be able to do those computations without a calculator. All right, so if we put all of this information together, let's see, I have to approach the asymptote, but connect all of those points. Remember, I can cross a horizontal asymptote, unlike the vertical asymptotes. So it crosses there at the origin, connects those points. Notice I do have my extrema. The highest it goes and the lowest it goes are at those extrema. It does change concavity. Notice how it changes from concave down to concave up. Concave down to or concave up to concave down. Make sure you recognize that it is changing concavity at those inflection points. And then finally, of course, it does approach the asymptote. And across the both x and y axis there at the origin, at that intercept. And so there you go. Ta-da! There is our lovely little graph. Enjoy!